Thank you. Thanks for your kind introduction, and thanks for inviting me. I'm a big fan of the research you're doing in this institute. I'm following as much as my capacity allows your research. So when I got the invite, I did not hesitate to say yes, and I'm very excited to be here. So thanks for that. I also feel home here in Sweden. I did my PhD in Sweden, and I learned important lessons to be humble and work hard in Sweden. Okay, so I hope the audience online also hear me well. If not, okay, great. So we have a small team at the moment in Graz and Vienna. We have a couple of 5 postdocs, 5 PhD students, and we recently got a ERC grant in network fairness. So if you are interested, please follow our research and feel free to contact me if you want to come to a research visit. We are also hiring. So let me give you a kind of overview of my research, and then we go to different sections of my research, and then you can ask questions after each section is finished. So me and my team are interested in understanding how social mechanisms in micro level affect group identity and group formations. And these micro level mechanisms can be self-selection biases, I don't know, homophily, triadic closures, and so on. And these mechanisms in the micro level create macro level kind of structures that are very interesting because these are non-random structures. And these structures are so important because it affects the formation of culture, it affects the spread of information, it affects how we perceive others. And nowadays, this information in this structure are being fed into online systems and AI systems. Systems such as ranking system or people recommender systems use this information encoded in our social networks to rank people, to give recommendations of what papers to read, what scientists to follow, and so on and so forth. And also, as a result of interaction between other people and the AI, we are basically adopting our opinion, our behavior, and this is basically we are dealing with a path-dependent, dynamical, complex systems. So my goal is to use techniques and methods in complexity to understand this kind of a complex adaptive system. And I think we have great tools in our hands. So let me give you some definitions, what for example, I mean by minority or inequality. In social sciences, it's discussed that the structural inequalities are one of the key drivers of inequalities. And usually structural inequality means that you have members that are part of multiple interconnected social categories, and they are also embedded in a system of power and privilege, and this creates structural inequality. More concretely, I'm interested in structural marginality, in the ways in which a structure affects and marginalizes certain groups of people in society. And nowadays, also, again, with AI algorithms, this effect can be reinforced and exacerbated sometimes in a way in which we cannot comprehend. So structural inequality can have secondary effects together with AI and algorithms. Now, what do we mean by minorities? More specifically, I mean numeric minorities. One or multiple groups in society that are underrepresented numerically compared to other groups. Good example of this is, for example, people of color or women in the STEM fields, that they are minorities, and as part of kind of investigation in complex network, we ended up studying a lot the situation of minorities in academia. Okay, so let me now give you an example that kind of illustrates, maybe to give you kind of a story of my research. So let's assume we have Sarah. Sarah is a mathematician. She is also a parent, and she's also an immigrant. Sarah noticed that her papers don't get so much citations and visibility as compared to her other colleagues. She's also not usually invited to exclusive research visits and collaborations, and she's wondering what's happening. In a broader picture, the situation of Sarah and other minorities is that they are not distributed randomly in social graph, in collaboration networks. Rather, we see situations like this, where there is a homophily among the majority and homophily among the minorities. And this homophily especially penalize groups that are smaller in size compared to other groups. And very, very nice kind of survey explaining what happens when you have this kind of situation is written in this very nice survey by DiMaggio and Gary that illustrates that this kind of structural marginality affects access to healthcare, education, job opportunities, and so on and so forth. So now this kind of a structure affects also ranking algorithms. So what we have observed is that minorities might not appear in the top rank compared to what we expect from their size. But more importantly, there is a constant feedback loop between what we click and the structure of our graph. So over time, through this feedback loop, maybe some groups become even more peripheral compared to the initial condition. So as you see, over time, things deteriorate. Visibility of minorities deteriorate. And there has been recent empirical research that showed that this actually really happens in terms of job opportunities. So what's happening at the moment in reality is that we are dealing with a situation that we have algorithms that makes things perhaps even worse for certain groups. And we need to understand this not in a black box way. So far, a lot of investigation on algorithmic biases in AI and machine learning communities are black boxes. We don't know why there is a bias, but we have to fix it. And we argue here is that we need to move away from this kind of approach, and we need to basically understand how social mechanisms drive these inequalities, because without such understanding, we cannot really correct algorithms and biases. In a broader context, why should we care about structural marginalization? There are, of course, many reasons. Two of them that I can name is that one is that if we want to solve, if we want to find innovative solutions for complex problems, we need diversity. And more importantly, as we live in a complex, interconnected world, this inequality and suffering of certain groups affect all of us in one way or another. So we need better societies. Okay, so in our research, we are focusing on a variety of aspects of inequalities that happen in our networks, and we call them network inequalities. One of them are social forces related to group identity, related to homophily and things such as rich gets richer effect. Some of them are space and time constraints, where we are and what time we are, which groups may affect opportunities and chances of interactions. Some of them are algorithmic forces, and some of them are historical forces. We might have certain effects in the past, but their breadcrumbs and effects are still present in the structure, although the actors might be different, right? And we like to look at these forces through computational tools to understand their effects on social networks and what happens kind of over time. Okay. Any questions? Feel free to ask questions. Okay, so let's start with the smallest building block of our social kind of connections, the way we connect with others, that is face-to-face interactions. And I think face-to-face interactions are very interesting building blocks of social connections because it requires both space and time constraints. So we need to be with the fact that I'm here now with you here means that we have excluded a lot of other opportunities to be elsewhere, right? So this is an opportunity, but also exclusion. So there is a time and space we offer to each other to be together. An example also could be this. For example, a poster break and so on. So what happens is that we might have some preferences to interact with other people, and this preference is combined with the pool of opportunities that is given to us in the space and time, and then there together we have something called like outcome homophily, something that we can actually measure. We go observe who is interacting with whom, and then we write it down. So sometimes it's very tricky to figure out from what we observe is that what is actually the intrinsic attitude of people towards others. And in this paper, we are trying to disentangle these two. So we are trying to disentangle the choice homophily that people have from the pool of opportunities using statistical methods in networks. Another very interesting example of a space-time is actually a paper that was just published this month, which I really liked because they showed that they looked at the Twitter friendship network and they looked at highways in the United States. And they found out that highways actually affect social connectivity between people. So really space and time are important factors. Infrastructure are important factors that can bond people or hinder people from interactions. We also recently, with our collaborators from the University of Chicago, we showed that there is a strong association between this spatial segregation and implicit racial biases in different cities in the United States. Okay, so going back to our basically face-to-face interaction, we used to have models of face-to-face interaction that suggest that individuals in a certain radius and proximity interact with others based on their attractivity. And attractivity is a value that ranges from 0 to 1, draw from a uniform distribution. So we decided to revisit that model and assume that what if there is also a homophily, meaning that people have color and that color also determines how people interact with each other. So in this case, the probability of two people in a physical proximity to interact is actually related not only to the attractivity of individuals, but also the homophily. That is a relational probability. And then we tested this model with 6 different data sets of face-to-face interactions with a very high resolution. So these data sets are temporal network data. So we know every 20 seconds who is interacting with whom face-to-face. And 2 of these data sets are contrast data sets, and 4 are school data sets, and the color is gender. So we have interaction between girls and boys or women and men. And what is interesting is that our model is able to reproduce the degree inequality we see between the 2 genders. And the previous model is a dash line that doesn't allow to basically explain the degree inequality between men and women that we observe in face-to-face interaction. What it means in a broader sense is that you can have a value of homophily that ranges from 0 to 1. 0.5 means neutral, meaning that yellow and blues are indifferent towards color. So they can mix independent of the color. So the average degree of the 2 groups fall to the same basic Gaussian distribution because it's a space and time constraint. We don't have a scale distribution. But then when homophily is high, minorities average degree basically fall behind the majority's average degree. And when there is a heterophily, meaning that minorities are attracting all the majorities, is vice versa. Minorities' average degree exceed the majority's average degree. So what it means is that all else being equal, just this intrinsic tendency of interacting with similar people, that is usually the case, can hinder certain group of people more than others. And this is partly related to their size. So if they would be 50-50, we wouldn't see this effect. But this effect now only penalizes one group more than the other. And this is very interesting in terms of asymmetries in inequality. Okay. Any questions so far? Okay. So now let's zoom out. Now we can discuss social networks, online social networks. Now, what is interesting about online social networks or citation networks is that these are often unbounded situations in which we don't have a space and time constraint. You can at any time contact whoever you want, connect to whoever you want, right? And this effect, this relaxation of space and time constraint create different kind of species of social networks. In the larger scale, you see a kind of emergence of a scale-free or skewed distributions. So this is the degree distribution of the groups, and you see more skewness. This is a logarithmic scale. So this deviates from this kind of a normal distribution. It's not sufficient anymore to discuss the average degree of the minority and majority. But what we can do, we can look at the degree distribution of the minority and majority and calculate the difference in the exponent. And that will tell us something about who is getting more advantage compared to the other group in larger scale social networks. So we are running a similar experiment, but now with larger scale networks, we are relaxing the space and time constraint, but we have other mechanisms such as homophily and Matthew effect, which gets richer effect because we don't have a bound. I mean, to some extent, we have some boundaries, but not as much as before. So again, we have a homophily parameter that ranges, and what you see here is that when homophily goes high, which is usually the case in a lot of organic social networks, the degree distribution of the minority falls behind the degree distribution of the majorities. And note that these are the nodes with the highest degree. And this is very important because when we rank these ranking algorithms, when we rank people, we are focusing on the top central people, individuals, right? So there is a lot of concentration here. To show this better, you can say that I want to rank individuals based on a degree rank. We can also call it page rank or other types of centrality. Top 10%, top 20%, top 30%. If in our experiments we have the minority group that are 20%, all else being equal, we would expect that they should appear in all the rank 20% of the time, right? So this is our expectation. But what we see in these experiments, if we have a homophilic network, when that parameter is 0.8, we see that minorities do not appear in the top rank compared to what we expect from their size. We are not here even doing intervention. We don't want them to appear even higher. We just want to make sure they appear as much as they exist in the system. And this doesn't happen. Okay. So this is one kind of that was a starting point of understanding why, for example, because this was basically started when my postdoc advisor asked me, there are these papers coming out in computer science that women do not appear in top ranks in, I don't know, LinkedIn, whatever jobs, important jobs. So why is this happening? The question is, okay, where do we start? And of course, coming from physics background, for me, it's important to start as with simple models, but mechanistic models, models that implement mechanisms to understand where things are going wrong. So this is an explainable model showing that only homophily and group size can create such situations. What is also important, given that some of you are analytical sociologists and you're very familiar with this cumulative advantage effect, is that we are actually dealing with multiplicative processes. So rich gets richer effect is a multiplicative process. Wealth is a multiplicative process. So these processes often generate skewed distributions. And what is very interesting about skewed distribution is that you have cumulative effects. cumulative advantages, but also cumulative disadvantages, and create things, and these effects make inequalities even worse, right? Okay. Any questions? Okay. You're suspiciously quiet. I hope that's a good sign.
We prepare the avalanche for the Q&A session.
Write them down. Okay. So now let's go to interplay between our social networks and AI systems. So to understand how AI algorithms affect our social networks, first of all, we needed to enhance our homophilic network model, make it a bit more realistic, because if you think about 2x follower-followee or citation graphs or hyperlinks, these are all directed networks. They have direction. And direction is important. It affects the PageRank centrality or eigenvector centrality and so on. So we kind of enhance the model using similar mechanisms to create directed graphs. And what is interesting about directed graphs is that now we can also study asymmetries in relationships. Maybe you have heard of, I think Coleman has a paper or book about asymmetries in life. So, for example, you can implement, you have these two homophily parameters, homophily that governs majority to majority interaction, homophily that governs minority to minority interactions. And you can have situations that both minority and majority are interested in majorities, or you can have both minority and majority that are interested in minorities, and so on and so forth. Okay, so now that we have better kind of representative graphs, we can look at some of these actual recommender systems. One of them is PageRank. PageRank is how pages in Google are sorted. It is also a fundamental mechanism in many other ranking systems, such as LinkedIn, general rank, or citation ranks, and so on. And then we have another algorithm that is called whom to follow. Is basically friend of friend, your friend mechanism. So and of course, it might be a variety of versions of this that companies use to recommend friends to you or people you may want to follow and whatever. But most of them follow the same principle. They know that you are more likely to be connected to a friend of a friend. So we ran these two algorithms on our graphs, varying the homophily and group size and asymmetries in homophilies. And we observed similar effects, meaning that minorities can be disproportionately become invisible if there is homophily in place, and even worse when there is asymmetry, right? If minorities are being penalized both from the majority but also from other minorities. But I think what is even more important when it comes to algorithms is the feedback loop. What does it mean? We have a social network like this, where individual I, with certain small probability, might want to connect a new link in his LinkedIn, right? He gets this recommendation, people you may know. And the recommendation, as I mentioned to you, is often the neighbor of her friend. So she gets this recommendation, and with a small probability, she might accept one of them. And she might ignore an very old friend. So what happens is that in the next trimester, now she has a new link, right? So what does this mean in our social network in a kind of, if we run this feedback for 100 generations in terms of time? What we get is something like this, where this friend of friend recommendation makes our social graph, social network more segregated, more cohesive, but also more segregated, right? So, for example, what we observe, one of the things we observe is that we are asking what rank position should I go until I see minorities that are represented in the graph? So if minorities are 30%, how much in the rank should I go to see 30% minority? In the beginning of the simulation, the first trimester, if you go up to the 56% of the rank, you see 30% of the minority as you expect. But interestingly, if this feedback loop continues, you may need to go to the 70% of the rank to see 30% of the minority. And this is very interesting because this shows that effect of algorithms are non-linear in the long term, meaning that if we would have stopped here and project this for future, that yes, algorithms have this effect, we would have underestimated how much it can actually make a difference in the long term. So this path dependency and long-term dynamics, I think it's very important when it comes to assessing risks in AI systems. So in this paper, we argue that because AI Act has a strong emphasis on risk assessment, but we have risk assessments, we can talk about long-term risks or short-term risks. So what do we do for the long-term risks of algorithms? Do we need to wait for 10 years to see how algorithms are messing up with our life in order to figure out what to do? We argue that here maybe we can use also computational models to kind of forecast, to see, okay, if this thing going on for another 10 years, what will happen? And then do some more active role in terms of designing better algorithms that do not exacerbate such inequalities. Any questions? Yes.
So, no, just kidding. But like with the last thing you said, right? You mentioned like, okay, we have the DSA in Europe, and we have like other means to kind of like try to assess, okay, what is going to happen, and that there are these long-term risks with AI systems, right? When you have these recommender algorithms. The question is that I had to immediately think about was, shouldn't we kind of like require this kind of stuff for basically any algorithm? Because I would imagine that any, even like very, very rudimentary and basic algorithm could also exhibit these things, right? Because everywhere where you have, I don't know, like a social network and then something, even if it's just like an if-else statement that operates on that structure and causes some change, could in theory exhibit kind of like the same amount of risks, right? And the question would be, do you have any kind of like grasp on like how different it might be when you have something AI versus kind of like more classical engineering in social networks?
I don't understand.
Yeah, I've been thinking like this Twitter algorithm, PageRank algorithms, all of these are kind of just like relatively simple and straightforward algorithms of how users are being recommended to each other, right? And now that we have these AI things, and like, I mean, the Digital Services Act is primarily aimed at these kind of like new AI enhanced things that are like, how different are they from kind of like the more classical algorithms that can kind of like exacerbate inequalities? Like, how different is the risk that kind of like generative AI, for example, would have when it comes to these kinds of like mechanisms? Do you have an intuition? Do you have like some thoughts on that already?
No, but I have to say, the fact that these algorithms affect our social network is already not trivial. I mean, there is a lot of a lot of work in AI and machine learning communities. If you look at, they are dealing with what's called as tabular or non-relational data sets. There is a test. Is test biased towards certain groups or not? No, they deal with everything at the moment in a non-relational way. But we already social networks is one step ahead, meaning that there can be relationship between actors and identities, and this can have also effects on the algorithms. So first we need to establish that, and then the next step to say that what would be the long-term consequences of these relational kind of processes. on algorithms and so on. So we are a bit, I have to say, we are a bit ahead. At the moment, this AI Act and Digital Service Act really deal with simpler, tabular-based data sets, and we still have no clue many of the cases how to deal with it. So I think we still need a lot of time to develop it. Yeah. I might not have answered your question very well, but I'm happy to discuss more.
No, I think that was really interesting, because I never thought about kind of like, okay, what was the kind of like assumptions underlying kind of like what they wrote into these laws. Mm-hmm. So that's already like pretty interesting.
It is clear if you read the AI Act, it's very fuzzy. There is no clear understanding of how to assess something is minimal risk or unacceptable risk. So it's our task, I think, as scientists to kind of open this kind of fuzziness and try to shed light on describing what processes could be unacceptable risks and what to do about it. Okay. Okay, good. So one forces that I also mentioned in the beginning of my talk is temporal forces, historical forces, right? You might have processes in the past that has discriminated certain groups in the population, and they might have their footprint to the current structure and possibly future structure. And that brings us to the studies of women and minorities in science, because it turned out that we have a lot of studying scholarly databases is one of the most comprehensively documented databases of human collaborative endeavor. So that brought us to study American Physical Society is one of the largest databases of physicists publishing papers in a variety of journals in American Physical Society. And this data I'm showing from 1950s here, but basically we have 100 years of data here of participants. And then we have annotated gender based on very fancy tools of combining first names, but also images of the scholar that we could collect from Google image and then infer from the faces, the gender, which turned out a much better method than using baby names, first names. So after doing that, we wanted to study how men and women collaborate in academia and physics. What is striking is actually the participation of men and women in physics. So there is, of course, a lot of discussion that women's are increasing in physics, but as you see, men increase even more. So actually, the gap is not closing. And so this is number of authors, and I believe unique authors that publish in American Physical Society over the years. So in this paper, we show that a lot of these discussions about citation disparities between men and women are just the byproduct of slow arrival and late arrival of women to the science. So it might not be really a bias towards not citing them, but they simply have a slower arrival. And usually when you have two competing papers that have similar topic, the first mover paper get more citation than the other one. And we show here that a lot of this kind of gender biases in citation can be associated with the late arrival and early arrival of. Okay, but what does this temporal effect mean in terms of other processes, dynamical processes? So if you look at this collaboration network of men and women over time, this is we use the real data. So each age is the publication, is a collaboration between two scientists, and the timestamp is the year that they have published the paper together. So if you have a process like this, that minorities are in the beginning are very few and they're slowly, gradually increasing, what happens to spread of novel ideas, information? What happens to spread of knowledge? Maybe even job offerings, no? Because a lot of these processes are social processes. We discuss with our colleagues, do you have a good PhD student? And we seal the deal. So we looked at this temporal collaboration networks of physicists, and then we run this simple information spreading dynamic on them. And we assume, how does it work for women to access the knowledge when it arrives to them? How does it diffuse if the starting point is a woman as compared to men? And of course, it's calibrated by their size in that time window. What we found is that you can look at the results. This is a recent work, and I'm happy to discuss more. What we found is that when it comes to diffusion, if the knowledge starts from a woman or man, with the same probability and speed, it goes to the rest of the population. But if the knowledge starts from a man, it sometimes takes a long time to get to women. And so we are trying to figure out what's going on. It's probably also related to this kind of a slow and late arrival of women. But I think this is very consequential when it comes to spread of novel ideas or job offers or whatever. Okay. So by now you have guessed, I guess you have asked this question. We don't live in a binary world. It's not man, women. It's much more diverse than that. Yes. We are dealing with a multidimensional kind of networks, right? And it's very complicated. One of the complications is what is called as consolidation in social networks. Maybe you have heard it if you're a sociologist. So consolidation, if I want to really make it simple, is as follows. You have in this scenario 9 women, 9 black, 9 white, right? And there is, I would argue, there is no correlation between gender and race here. But you can have these situations where in the aggregate, you still have 9 women, 9 black, and 9 white, but you have consolidation between race and gender. So there is obviously a correlation, diagonal correlation between these two attributes, right? So this is one of the complications when we have multidimensional networks. And then, of course, there is big other kind of complications. You have gender in one axis, and then you have, let's say, nationalities A, B, and C in another axis. And then individuals somehow in their brain calculate how is this? Gender is important for me, how much nationality is important for me. Then you have 2 homophily for gender and nationality, and then somehow you aggregate these mechanisms in your head, and then you create a link, right? And we did some experiments with this aggregation mechanism. It's not so obvious. You could sum these 2 directions. You could sum homophily in gender and homophily with nationality. You could multiply. You could take an average. You could maximize one of them. And what is interesting is that the choice of aggregation affects the topology of the social network. So if people use AND function, we call it AND function, meaning that you multiply in every dimension. These are picky individuals. They want to make sure they find the right person who has the right gender and right, stochastically speaking. Then you end up to having such kind of networks. But if you have all function, that one dimension, satisfaction in one dimension is sufficient, you have this kind of graphs, right? So we developed this model, but also we tested with real data, with the ad health data in the United States, because this is like, we have more or less 70 independent experiments of friendship in schools. So that can serve us to basically infer what types of aggregation mechanisms and what types of model are best explaining the way we aggregate our social networks. We aggregate this homophily in multi-dimensions and connect with others. Now, can you guess which of those aggregation mechanisms better explains the social networks we observe? And yeah. And yes.
In schools, I would say, but in other places, maybe.
Yeah. So In these recent works, we have looked at this aggregation function, trying to use inference models also to kind of infer it with real data, but also we study inequalities that comes from intersection of multiple categories. And this is, I think, is very important because it can bring us towards understanding intersectional inequalities in social networks, something that has been discussed a lot in the literature, but quantitatively speaking, hasn't been done much. And we are trying to kind of really use a quantitative way to show that emerging inequalities exist, and it's not simply the sum of inequality in every dimension. What we found is that in some cases there are some inequalities are just the sum of the multiple dimensions, but in many scenarios there are really emerging inequalities that cannot be predicted by the sum of the inequalities in every dimension. Okay. Any question? Comment? Yes.
So which one? I didn't understand. Which one was the best predicting?
And
Okay.
It does depend on the. Did you say that you calibrate the degree of correlation?
yes.
You took the observed one. Yeah. Yeah. Well, I was curious if it changes with the. Depending on the degree of the correlation, I guess these functions might produce different things. I know in Nassau's work, they used a different function, which I think was the closest in any of the dimensions.
Mm-hmm.
And they, I think they find that they also, I think that kind of function also produced the clustered network as well.
Yeah.
But it depended a lot on the level of correlation. Under some circumstances, produced like small well networks.
Yeah.
And then other ones more wide bridges between the.
Yeah.
In your case here, would you assume anything about how simple or complex contagion here, or which kind of contagion are you using?
We don't use contagion,
Yeah.
but apart from the aggregation function, it's just random. So these are random graphs. So you can call them like a generalization of block models or random exponential random models. So I think it's actually pretty comparable with those models. Yeah. And it's interesting because we also found agreement with the cross-categorization literature, which is a kind of a these are the psychologists who run experiment asking people, if you have this scenario, who would you pick and how would you? And then they also found that this AND function is more explaining people's choices in terms of forming ties. Yeah. Yeah.
And do you think this would generalize to most cases, or have you tried to extend that to? I think schools are very peculiar because it's a specific setting.
Yeah.
But yeah, what do you think about other?
That we would love to do next. Yes.
Okay.
Yes. Yes. We definitely need to look at other systems. Yes.
But do you have assumptions, or do you just?
No, we don't make any assumptions. We just we have this couple of aggregation mechanisms, and then in all of the cases we just use them and use inference, network inference, and then check which one explains best the observation.
And was it good at explaining it, or
the AND function? Yes. I mean the extent of explanation is of course varies a little bit because we have 70 different schools, right?
Okay.
But in aggregate level, AND was the most explainable function in majority of the cases. You can also have you can of course have a look at the paper. There's a lot of details there. But there is also one interesting thing is that this also method allows us to say which categories are actually important. Because we had gender, race, and grade, I think. Grade. And it turned out, actually, you could eliminate gender and you could still explain the social ties. So it turned out gender is actually not important. What was more important is race and grade. This is just for explanation. I haven't shown you the grade. Yeah.
That was just with the degree distribution, or what were you trying to match? What feature of the network were you trying to match? Just the degree distribution, or?
In this case, yes, the degree distribution.
So you're saying gender didn't matter for the degree distribution?
Gender did not matter in terms of explaining the social context, basically. Okay. Okay, so until now, I told you how inequalities exist in our social networks and affect algorithms. The question is now, what do we do? Can we do something about it? What can we do? And that's also part of what I plan to do in my ERC for the next 5 years, to define fairness for networks, because at the moment, again, in AI community, we talk about individual fairness or group fairness. There is no discussion about network fairness. So we need to define it. Who are the stakeholders? What are the ethical goals? What are the moral values? Because again, it's a big wild west at the moment in our community. Everybody come up with a new fairness measure, but why? Who are the stakeholders? What are the objectives? It's not clear. So that's where we plan to go. But maybe I can tell you what this type of simulations can help us to kind of also discuss policies and interventions for the future. For example, think about a scenario like this. This is a real scenario of CEO meeting in Germany. And this made it to the news. I don't know if you're from Germany, you maybe heard about this picture in 2022. So nothing looked like has changed, although participation of women in corporate boards have dramatically changed over the 100 years. The question is that why minorities are not in the top network positions? And what interventions are actually helping us or not. So this situation then can be simplified in a growing graph, kind of growing network scenario. We have a growing network, and minorities and majorities arrive with certain probability. Let's say here minorities are 10% of the population. And then we introduce intervention. We introduce quota. We say that from now on, 90% of arrivals should be minorities, which is very extreme, unrealistic, but for the sake of explanation. Another intervention we could introduce is behavioral intervention. We can maybe we have some classes for top managers or some regulations in the hiring. Not in the hiring, but top managers that allow them or asking them to collaborate more with minorities, or also with minorities to collaborate more with majorities. And then, although the size of the minorities are growing, but we are interested in the people in the top of the network rank, right? We want to see, do they become representative in the top rank in networks or not? And what our experiments show is that you can have extreme quota, but that doesn't guarantee minorities will climb the network rank as compared to what we expect from their size. But you can have mild group size intervention with behavior intervention, and that achieve much better goal in terms of bringing minorities to the top rank. So I think this kind of a computational simulation models can be used in a more productive way in terms of arguing what kind of policies do we need, what policies are working, what policies are not actually working or doing anything, and hopefully help us to make the networks better for everyone. So I hope I convince you that we have network models are instrumental tools to address societal problems. And I want to thank you and mostly my collaborators and students, because without them, I cannot do any of this fantastic work. Thank you so much.